Welcome to Advanced Group Theory. Today we are diving into a fascinating and essential topic called commutator subgroups. If you have ever wondered how mathematicians handle complex systems where the order of operations fundamentally changes the final result, you are in the exact right place. We are going to build this concept entirely from the ground up. So let us get started. Now that we know our goal, let us think about packing a suitcase. If you pack heavy shoes first and delicate clothes second, the result is very different than doing it in reverse. In mathematics, when the order of operations changes the outcome, we call the system non-abelian. But how do we measure exactly how much the order matters? We use a mathematical tool called a commutator. It captures the exact messiness or difference between doing action A then B versus B then A. By collecting all these individual measurements into one mathematical bag, we create what is known as the commutator subgroup. So, how do we write this measuring tool mathematically? The commutator of two elements, A and B, is formed by multiplying A, then B, then the inverse of A, and finally the inverse of B. If the group is perfectly commutative, the elements and their inverses will just cancel out completely to the identity element. However, in a non-abelian group, this specific combination leaves behind a mathematical remainder. This remainder tells us exactly how far the elements are from commuting. It acts as a highly precise mathematical detector for non-commutative behavior. If the variables change, the remainder changes accordingly. Building on our mathematical detector, we can now define the commutator subgroup itself, which is denoted by the symbol G'. The angle brackets you see are a standard mathematical notation, meaning the subgroup generated by the elements inside them. We must use the generated by operation because simply multiplying two commutators together does not automatically produce another simple commutator. By taking the generated subgroup, we ensure that our collection of elements is mathematically closed under both multiplication and inversion, forming a valid, complete subgroup that captures all the messiness. Before we move on to complex proofs, let us see this with a concrete example. Let us find the commutator subgroup of an arbitrary abelian group, like the integers under addition. This will serve as a baseline. We start with the standard definition of the commutator. Because we are working inside an abelian group, the order of multiplication never matters. This means we are allowed to swap the sequence A times B with the sequence B times A. This simple swap is the critical step that positions the elements right next to their respective inverses. Continuing from our swapped sequence, we know that when an element is multiplied by its own inverse, they annihilate each other to produce the identity element, E. The A and A inverse cancel out. The identity element acts like the number 1, so it does not change the surrounding elements. We are left with B times B inverse, which again results in the identity element. This proves that every single commutator in an abelian group evaluates to the identity. Our trash bag of messiness is completely empty, which perfectly matches our intuition. Now that we have seen an abelian group, let us examine a non-abelian group, specifically the symmetric group on 3 letters, S3. This group represents all possible ways to shuffle 3 distinct objects. We will pick 2 specific elements that we know do not commute. The element A, which swaps the first and second objects, and the element B, which swaps the first and third. Because these are simple 2-element swaps, they are their own inverses. Let us plug our chosen permutations into the standard commutator formula. Since each element is its own inverse, the formula simplifies to repeating the 2 elements twice in alternating order. We must now multiply these permutations together from right to left. By multiplying the first 2 swaps on the right, we get a cycle that shifts all 3 numbers, specifically the cycle 1, 3, 2. Multiplying the second pair on the left gives us the exact same cycle again. For our final step, we multiply the cycle 1, 3, 2 by itself. This results in the reverse cycle, which is 1, 2, 3. This final result is not the identity element, which proves that our original two swaps did not commute. This specific cycle generates a subgroup of size 3, which is the alternating group A3. Therefore, the commutator subgroup of S3 is exactly A3, containing all the even permutations. Having calculated some actual commutator subgroups, we can now explore their deeper properties. A crucial property is that the commutator subgroup is always a normal subgroup. To prove this, we must show that it is invariant under conjugation. Conjugation means taking an element, multiplying it by a group element on the left, and that same element's inverse on the right. If the subgroup is normal, this operation will always trap the result back inside the subgroup. Let us prove this normality property mathematically, step by step. We start by writing out the conjugation of a standard commutator by an arbitrary group element G. We simply expand the definition of the commutator inside the parentheses, placing G on the left and G inverse on the right. To move forward, we use a clever algebraic trick. We insert the identity element E between every single variable inside the parentheses. Since E is exactly equal to G inverse times G, we can place this combination between A and B, between B and A inverse, and so on. This sets up our next crucial step. Continuing with our expanded expression, we now group the terms together using parentheses. This transforms our single long string into a product of 4 individually conjugated elements. Looking closely at these 4 grouped terms, we recognize the exact mathematical pattern of a commutator. It is the commutator of the element GAG inverse and the element GBG inverse. This proves that the conjugate of any commutator is simply another commutator. Because the generators of the subgroup behave this way, the entire generated subgroup is indeed normal. This completes our proof and leads us to our next major concept. So, we have proven that the commutator subgroup is normal. This brings us to its most powerful feature. It forces the creation of an abelian quotient group. A quotient group, denoted as G over G prime, is formed by grouping elements into cosets and treating those entire groups as new single elements. We want to prove that in this new group, the order of multiplication does not matter. We will multiply 2 cosets in one order and show it equals the reverse order. Let us set up the proof to show that this quotient group is indeed abelian. We start with the standard rule for multiplying 2 elements in a quotient group. When we multiply the cosets AG prime and BG prime, we simply multiply their representatives A and B together and attach the normal subgroup G prime to the result. We now need to find a way to flip the A and the B inside the parentheses. To do this, we factor out the reversed product BA to the front and immediately follow it with its inverse to keep the equation perfectly balanced and mathematically true. Looking at our newly balanced equation, we focus our attention on the sequence of 4 elements that immediately follows the BA term. This sequence is exactly the definition of a commutator, specifically the commutator of B inverse and A inverse. Because it is a commutator, it is by definition an element of the commutator subgroup G prime. This is the crucial moment in our derivation where the non-commutative messiness is identified and isolated into a single mathematical term. This isolation allows us to handle the messiness directly in our final step, connecting this algebra to the core property of quotient groups. For our final step, we use a key property of quotient groups. If you multiply a coset by an element that already belongs to the normal subgroup, the coset absorbs it completely without changing. Since our isolated commutator belongs to G prime, it is absorbed and effectively disappears from the equation. We are left with only the reversed product BA attached to the subgroup. This proves that the multiplication order can be reversed without changing the result, meaning the quotient group is perfectly abelian. We have successfully hidden the messiness away, completing our derivation. Let us visualize what we just proved. On the left, we have our original, messy, non-abelian group G. The smaller circles inside are the cosets, including the commutator subgroup itself. Notice how complex the elements inside each coset are? But follow the arrows to the right. By treating the entire commutator subgroup as a single identity element in the new quotient group, all that non-commutative mess is hidden away. The resulting structure on the right is perfectly well behaved, simplified, and commutative. We have covered a lot of ground today. Remember, the commutator subgroup acts as a mathematical container for all the non-commutative behavior within a group. By gathering these elements, we create a normal subgroup that perfectly captures the system's messiness. When we quotient out this subgroup, we are left with a perfectly abelian structure. Understanding this is key to unlocking deeper structures, from solving polynomials in Galois theory to understanding Heisenberg's uncertainty principle in quantum mechanics. Great job following along.